Hey everyone, this is a lesson on related rates in calculus, and this lesson is kind of interesting. It's just an application of the chain rule, and just to go over a couple of things, finding the rates of change of two or more related variables that are changing with respect to time. That's when we want to use related rates here. We want to differentiate both sides of the equation implicitly with respect to time. So after the differentiation step, what we want to do is substitute the values for any quantities that depend on the time. So phrases that will kind of represent derivative with respect to time would be like how fast or how slow, or at what rate something changes, and things like that. Okay, so that's an indication to use a related rates question, or when we're looking at related rate questions. Okay, these are just some common formulas. Area of a circle, circumference of a circle, volume of a sphere, volume of a cone, volume of a cylinder. We know our Pythagorean theorem, right? Just a couple common Pythagorean triples. So a lot of the times when you see these like volume of a cylinder, they're going to be given to you on the AP exam in the context of the question, okay? So let's take a look here. We're going to go through just a couple of questions just so you can get the idea of how this works. It says here, let A be the area of a circle of radius r, and assume that r increases with time t. At a certain time, I'm sorry, at a certain instant, the radius is 5 centimeters and is increasing at a rate of 2 centimeters per second. So how fast is the area increasing at that instant? So you can see here a couple indicators. This is a related rates question. Okay, so a couple things that are given in the question. Let's see. We are given the, let's see, at a certain time, the instant that the radius is 5 centimeters, it's increasing at a rate of 2 centimeters per second. So that means that the radius is changing at that rate, okay? And that's what we would say dr dt, okay? Because this is a rate that it's changing. And so we said it's changing by 2 centimeters per second. All right, we also know that at that instant, the radius would be 5 centimeters. And it says here, what are we looking for? How fast is the area increasing? So that would be dA dt. Again, what's the area changing, or what is the area in terms of time? Okay, so I'm going to put your dA dt. That's what we're looking for. All right, so in order to do this, let me start by writing the area formula for a circle. So I always like to start by figuring out what I have. So area of a circle is A equals pi r squared. And now all we want to do is derive implicitly on both sides. So if I derive this A, I'm going to get dA dt, okay, equals 2. Now here we can just use a power rule. So this is going to become 2 pi, all right? And this r now becomes a power of 1, but we have r, of course, and we just derived r. So let's put here dr dt. All right, now that we've derived implicitly, we should be able to plug in our particulars, okay? We're looking for dA dt, so we don't have anything that we can plug in there, but we do know the value of r, right? That's 5. So I'm going to say 2 pi times 5. And we also know dr dt. That was the rate at which the radius was increasing, right? And so that's going to be a 2 that we plug in here. Okay, now we can just multiply this across. 2 times 5 is 10. 10 times 2 is 20. And so we end up getting 20 pi for basically how fast the area is changing at that instant, okay? So 20 pi, we can put this as our answer. We're going to go ahead and put here a unit. So this is centimeters square per second. All right, a lot of the times these related rate questions, they want to get our unit in there. So that would be our unit. Okay, let's bounce around here. Let's do a few more. We have let L, let's put this as L, let L be the length of the diagonal of a rectangle whose sides have lengths x and y, and assume that x and y vary with time. So if x is increasing at a constant rate of 1/2 feet per second, well then that's a given, right? That's dx dt, and that we know is positive because it's increasing. That would be 1/2 feet per second, okay? And y is decreasing at a constant rate of 1/4 foot per second. So let me put dy dt, and that's decreasing. That would be minus 1/4 feet per second. Okay, how fast is the size of the diagonal changing when x is 3 and when y is 4? Is this diagonal increasing or decreasing at that instant? So these are the given pieces of information, and what we are looking for here is how fast is the diagonal changing. So ultimately, we are looking for dl dt, right? That's what we're looking for here. So let's figure this out here, okay? All right, so this looks to me like we can start off with our Pythagorean theorem. So I'm going to say here x squared plus y squared equals to L squared. Alrighty, and just use a power rule on this when we derive implicitly. So when we derive x squared, we're going to get 2x dx dt. All right, when we derive y, we're going to get 2y dy dt. And again, every derivative here is in terms of time, which is why we're always putting all our derivatives over dt. And then oh, I'm sorry. And when we derive this L, we get 2L. Ooh, 2L. And we'll go ahead and say here dl dt. Okay? All right. So we got this ready to go. And remember, we're working on isolating dl dt. Okay? So let's plug in our particulars now that we've derived implicitly. We know that x is 3. So this is really 2 times 3. Dx dt was 1/2. So I can plug that in. Plus, let's say we got this 2. We know that y is 4. Dy dt, that should be negative 1/4. Okay, equals 2. And then we have here 2L. Hey, do we know what L is? Let's see. Could we maybe figure that out? If x was 3 and y was 4, that should be one of our Pythagorean triples, right? And one of our Pythagorean triples should be 3, 4, and 5, right? And again, you saw that in the beginning of the video here, okay? If not, you can always do 3 squared plus 4 squared equals L squared using Pythagorean theorem, and you will in fact get 5. All right, so we'll find L just like that. So we get 2 times 5, and then we have that dl dt. All right, so with that now, we're going to go ahead and isolate dl dt. Whatever we get here, we'll just divide by 10. All right, these 2's should cancel. These 4's should cancel. This leaves me with 3. This becomes minus 2, right? So 3 minus 2 should be 1 equals to, this is 10 dl dt. And now we just want to divide both sides by 10. And we end up with dl dt is just equals to 1/10, right? Now we need a unit, right? Now, just like the x and the y were feet per second, well, that means that the diagonal here is changing at a rate of 1/10 feet per second, okay? So that's the answer to that. Now, notice that my answer there was positive, right? And so to answer the second part, is this diagonal increasing or decreasing? This diagonal would be increasing, okay? So if it's positive, it would be increasing. If it's negative, we know that it would be decreasing. All right, let's do a few more here. Suppose that z equals x cubed y squared, where both x and y are changing with time. So this one's interesting because it gives us like our own formula that we want to use. Remember I said that a lot of the times they'll give you the formula that they want you to use for the related rates question, okay? But x and y, they're changing with time. So at a certain instant, when x is 1, then we know that y is going to be 2. Now, we can't plug that in yet. We have to derive implicitly first. It does tell us that x is decreasing, so that means dx dt. That's right, that's a rate. X is decreasing at a rate of 2 units per second. So let me put here minus 2 units per second. I know it's kind of a weird unit, but that's what we'll use. And y is increasing, so this would be dy dt. At a rate of 3 units per second. So let's put here 3 units per second, okay? All right, with that being said, how fast is z changing at this instant. So we're looking for dz dt. Alrighty. Okay, here we go. And again, how fast, that indicates related rates. So we're going to derive this implicitly. That means we're going to get dz dt equals, when we derive, oh, by the way, this right here is a product rule, right? Remember, your product rule is f prime of g plus g prime of f, where you say f and g are the two pieces here, right? Okay, so let's start with the derivative of x cubed. That's just going to be 3x squared dx dt. And we want to multiply that by y squared, because that's just the first part of the product rule right there. Okay, plus now we're going to derive y squared. So that gives us 2y. And again, dy dt, because all these derivatives are with respect to time, times, and then we need to get that x cubed in there. And the reason for that is that's just the way the product rule works. It's the second piece to that, okay? All right, now that we've derived implicitly, we are ready to plug in our particulars, right? So this tells me that dz dt would equals to, let's see, x is going to be, we said 1. So that's 1 squared. We know that that's 1. So let's put here 3 times dx dt. That's negative 2. Y is going to be 2. And so 2 squared should just be 4. Okay? Plus, let's do the rest of this. So 2 times y, which is 2, dy dt, that is 3. Okay, and x cubed, remember x was 1, so 1 cubed is just 1. I don't think we need to multiply by 1. We are good. Okay, so 3 times negative 2, that should be negative 6. Negative 6 times 4 should be negative 24. And then over here, 2 times 2, that's 4. 4 times 3 should be 12. And we end up with negative 24 plus 12, which should give us negative 12 units per second. Now, what is this? Remember, this is dz dt. Okay, notice I'm putting that unit every time, right? And the reason for that is these typically do come out every now and then as FRQs, and the units do usually get you one of those extra points, okay? All right, is z increasing or decreasing? Well, I see it's negative, which means it would be decreasing, okay? All right, let's do another one here. Air is being pumped into a spherical balloon at a rate of 5 centimeters cubed per minute. Determine the rate at which the radius of the balloon is increasing when the diameter of the balloon is 20 centimeters. All right, so what we want to do here is identify, as always, the given information, right? We know we're talking about a spherical balloon, and so typically you'll see these formulas given to you, but we know that we're talking about the spherical balloon. Let's see, this is determine the rate at which the radius of the balloon is increasing. And so for this particular question here, we want to use, well, we're looking for the rate at which the radius of the balloon is increasing, right? So that basically means that we're looking for dr dt. That's what that means, okay? But a sphere has that volume formula that we need to be 4 over 3 pi r cubed, okay? And so again, we usually have these formulas given to us, like in the context of the question. I just wanted to, give you the word problems as is, okay? So anyway, what else am I missing here? Oh, we know that air is being pumped into the balloon at a rate of 5 centimeters cubed per minute. Hey, that's the volume. So I'm going to put here that dV dt is 5, right? So that's centimeters cubed per minute. All right. We also know it says something about the diameter, right? Determine the rate at which the radius of the balloon is increasing when the diameter of the balloon is 20. Remember that when the diameter of the balloon is 20 centimeters, that should indicate to us that the radius should be 10. Okay, so indirectly giving us the radius is also a possibility, okay? Anyway, let's derive this implicitly. This is going to be dV dt equals to, this is just a constant, right? So because this is a constant and pi is also a constant, all we have to do is a power rule on this, believe it or not, okay? So to take this power, I'm going to move it over to the front as usual. So really I get 3 times my 4/3 pi, right? R to the power of 2 now, okay? Now remember that these should really cancel, okay? And that's going to leave me with 4 pi r squared. Now don't forget that we just derived r, which means at the very end of this, dr dt. Okay, that was the only variable here. Pi is just a constant. Okay, and so now from here, let's plug in our particulars. We know that r is 10, so this is going to give me 4 pi times 10 squared. That should be 100, right? And dr dt, that's what we were looking for, I believe, right? So let me leave that here, dr dt. Okay, and then on this left side, dv dt, that was the rate at which the volume was changing, right? We know that that was 5 centimeters cubed per minute. So 4 times 100 times pi, that's 400 pi. If I divide this to both sides, I get 5 over 400 pi, and that will leave me with dr dt. I'm sorry, yeah, dr dt. And this could be simplified, but remember in FRQs, there's really no need to simplify. Okay, so feel free to leave your answer like this. Now let's just talk about the unit real quickly here. The unit would be centimeters per minute. Okay, so kind of important here always to get that unit. You hear me mention it over and over again. Okay, all right, so we've done about 4 questions here with related rates. I hope you guys get the idea. Anyway, not too bad, but that's how it works. Okay, remember that all your derivatives, you have to derive them implicitly, and everything isn't, you know, you're deriving the variables with respect to time. Okay, let me just go back here for a second. I want to show you again. So differentiating both sides of the equation with respect to time. Okay, so every time you see one of those variables over dt when you take that derivative. All right, I cannot emphasize that enough. Phrases that indicate related rates, at what rate, how fast, how slow. If you go back and read through some of those questions, you'll notice that all those questions indicated those phrases, okay? And you cannot plug in your particulars, which means like that given information, until after you do that differentiating step. So that's why I wrote that in here. After the differentiation step, then you can substitute your values, okay? All right, hope it wasn't too bad. Hope you enjoyed related rates. And lots of more examples for related rates, because there's also that famous shadow problem. And of course, you have like volume of a cone and all those fun things that could go with related rates.